Welcome back to another video dealing with sequences and series. In this video, we're going to be talking specifically about what a series is and how it's based on a sequence. In this discussion, we're going to take several examples and work them out fully so that you can understand. I know that some of you have had sequences and series before, and you'll be familiar with the notation. You all should have seen some of the notation when you studied Riemann sums in Calculus 1. However, others of you may be very unfamiliar with the notation, so we'll go through it very specifically so that you can understand what each piece means. Let's go ahead and get started by sharing my screen with you. What you see now are my lecture notes for the section 5.2 out of the OpenStax Calculus book, volume 2. Now that we've discussed what a sequence is as an ordered list of values, we can move on to what a series is. A series is the real focus of chapters 5 and 6 in the OpenStax series. All textbooks tend to cover these topics in two different chapters, one focusing on the rules for deciding whether or not a series converges, and another for dealing with what are known as power series. First, we need to define what the series is and work through some of the terminology. We talked briefly in the previous video about sequences, about what a series is. A series takes the commas in the list of values out and replaces it with a plus sign. In other words, the series is simply the sum of all the terms of a sequence. So you're adding together all the values that are in the sequence. The notation for this uses the same notation as the Riemann sum, the uppercase sigma from the Greek alphabet. At the bottom, we indicate what the index is with the variable. Our favorites tend to be n as in Nancy or k as in kite. This one starts at n equal 1 and goes to infinity. This gives us an infinite sum of values where each value is given by the terms of a sequence a sub n. This gives us the sum of an infinite list of numbers a sub 1 plus a sub 2 plus a sub 3 forever and ever beyond a sub n, on to a sub n plus 1, a sub n plus 2, etc. Now, we've seen that a lot of sequences also start at 0, so sometimes you will see this notation starting at 0 instead of at 1. Again, for series just as for sequences, we either start with 0, 1, or some other integer value. When we're looking at these, this series, this summing together of all the terms of a sequence, creates yet another sequence called the sequence of partial sums. Now, what is a partial sum? Well, it's what it sounds like. It's part of this infinite sum. So it's only one part of it, and it represents the sum of the first n terms of the original sequence. So let's take a look at what that looks like. In other words, we start with some sequence. In this case, I started at n equals 0 for the sequence a sub n going to infinity. So we have an ordered list of values, a sub 0, a sub 1, a sub 2, a sub 3, separated by commas. There's an order to the list. There's a first, second, third, fourth, and fifth, and so on. Then to write the series, we will take out the commas and replace them with plus signs. So this gives a sub 0 plus a sub 1 plus a sub 2 plus so on forever and ever. And we write this with the sigma notation, uppercase sigma from the Greek alphabet. And you can write it either with k or n. Here I have k equals 0 to infinity of a sub k, but really I should probably have matched the k and the n that I have out there. They should probably match. Now let's take a look at what a partial sum does. A partial sum just takes part of this sum that we have right here. And the partial sum sequence always starts with S1. This is unlike a regular sequence, which starts at any positive whole number, or any whole number. They're not negative. They're not all positive. Zero is neither positive nor negative. But in general, sequences start at whole numbers, 0, 1, 2, 3, 4, 5. But the sequence of a partial sums always starts with 1, S sub 1, then S sub 2, then S sub 3, S sub 4. Note that these are all uppercase letters representing S for sum, which matches, of course, the Greek letter sigma, which is also the letter S in the Greek alphabet. Now, why are we starting with S1, S2, S3, Sn instead of starting with S sub 0? The subscript on the sequence of partial sums is telling you exactly how many terms from the original sequence that it's adding together. So this is not a sequence of infinite sums. Each one of these has a finite number of terms it's adding together. So S1 is just the first term by itself, A sub 0. S2 is the sum of the first two terms. That would be A sub 0 plus A sub 1, those two right there. S3 would be the sum of the first three terms, A sub 0 plus A sub 1 plus A sub 2. And you can see that this creates in itself yet another sequence based on the series. And the series, of course, is based on the original sequence, A sub n. Now, let's take another look at what S sub n represents. S sub n starts with whatever the first in the series is, and then goes out and it uses precisely the sum of the first n terms. Now, this is based on a geometric series where we have A first, and then A first times R, and then A first times R squared, A first times R cubed, and so on. So what we're looking at right here is actually a geometric sequence, which is equal to some value, A first, times R to the n. And again, we're going to start this at n equals 0 to infinity. You'll see that we're more often going to use 0 for the beginning place of the original sequence from now on. So we have this, and what we're doing is we're adding them together. So we're taking an infinite series. So the infinite series is going to start with n equals 0 and go to infinity of A first, whatever that constant happens to be, times R to the nth power. Now, what does the sequence of partial sums give you? Well, A first is S1. It's just the sum of the first term, which is just itself. And then S2 is the sum of the first two. And S3 is the sum of the first three. S4 is the first four, and so on. Notice that when you do Sn with a geometric sequence, that the last term has power n minus 1. That's because the first one did not have R. Actually, it had R to the 0th power. So this gives us the 1, 2, 3, 4, 5, all the way out to nth term in S sub n. So it is still the sum of n terms. So looking down here, you can write them in a slightly different form, which is just that S1 is A naught and S2 is A naught plus A1. These are the terms from the sequence, A naught, A1, A2, A3, A4. And this generates another sequence, which we can write inside the curved brackets, but note that the sequence of partial sums starts at n equal 1 and consists of uppercase S1, S2, S3, S4, and so on. This sequence of partial sums turned out to be super important. So you want to be sure that you understand where it is coming from. Now, why is it so important? Well, if you can think of it, in a sense, the sequence of partial sums is generating a list of values which can approximate the infinite series. And so the infinite sum can be approximated by this sequence of numbers. If this sequence of numbers approaches some value, then we'll say that the infinite series converges, and it converges to that value. In other words, when you add up infinitely many numbers, you get a finite number, which sounds kind of crazy, but it can happen. So if the sequence of partial sums converges, and that means it has a limit that exists, which means it must be a finite real number, then we represent that as S sub infinity And we write that the limit of n goes to infinity of s sub n is equal to s infinity. And that is what the infinite series is equal to. So we can represent it with the infinite series as well. So that means that this is also equal to the sum from n equal whatever it happens to be, 0 to infinity, of a sub n. In other words, s infinity ends up being equal to this series if the limit exists. If the limit does not exist, then we would say that this series diverges. Now, one of the things that we will need to be able to do while we're working with series is to be able to change the lower limit of summation. And the reason for that is there are some formulas for different expressions in the summand, different values or rules for giving the sequence, particularly for n squared, n cubed, things like that. We have some formulas, but the formulas start with the lower index of summation being 0. So we want to be sure that we know how to convert any infinite sum into one starting at 0. So this is best seen by looking at an example. So we're going to start here with example 1. In example 1, we have the infinite sum from k equal 5 to infinity of k squared over k plus 3. And we want to rewrite this so that the lower index of summation is 0. So we want it to go from k equals 0 to infinity. And again, the choice of k or n is completely arbitrary. You can use n if you like that instead. And you'll see here that I kind of used n here and k here, but really I mean the same thing. So we want it to start at 0. Now, there are various ways of doing this. I found that most of the methods that are covered in textbooks end up being very confusing, and they don't really seem to make much sense to students. So I have a different method that I use that sort of makes sense to students, and that way they're able to remember it. So this is the way that I teach it. Since the lower limit of summation in the original series is 5, and we want it to be 0, then we need to go backwards by 5, which means we need to subtract 5 from the lower limit of summation. So we're going to write 5 minus 5. That will give us 0 for the lower limit of summation. But I've changed things, right? So I need to compensate for this. And because I've subtracted 5 here, I need to compensate for that by pushing the expressions for k inside the summand, that's this expression here, forward by 5. So I'm going to put parentheses around these k's in the original expression, and I'm going to replace each of those k's with k plus 5. So I get k plus 5 quantity squared over k plus 5 plus 3, which of course leads to k plus 8. Now, does this generate the same values? Well, let's check it and see. Let's start up here with k equals 5. So again, this is, of course, the sequence a sub n, which is equal to k squared, or we could write it as n squared, over n plus 3 from n equals 5 to infinity. So I'm going to have a sub 5, a sub 6, a sub 7, a sub 8, and so on. This sequence, as originally written, starts with subscript 5. So if I'm going to write out the terms of the sequence separated by commas, instead of the terms of the sum or the series separated by pluses, I need to just substitute the subscript in place of the index, which is n. So 5 squared gives me 25. So I get 25 divided by n plus 3. 5 plus 3 would give me 8. So for the first term in the sequence, a sub 5, I get 25 over 8. Then I square the 6, which gives me 36. And again, I divide it by 6 plus 3, which is 9. And then I take 7 squared, which is 49, over 7 plus 3, which is 10. And you can see that we have a pattern developing here where the denominators are increasing by 1 each time, starting at 8, and the numerators are powers of the subscript, starting with 5. So we have 25, 36, 49, 64, and so on. Now let's take a look at our rewritten expression down here. This is a different sequence, but it generates the same list of numbers. So this could be written as the sequence B sub n, which is equal to n plus 5 quantity squared over n plus 8. But this starts at n equals 0 and goes to infinity. So let's write out what these values are. So again, we're starting with b sub 0 as our first term. So we'll have b sub 0, and then we'll have b sub 1, and then b sub 2, and then b sub 3, and so forth. So what do we get? Well, the first time we substitute in the subscript starting with 0. So I get 0 plus 5, which is 5, and I square it. So I get 25 over 0 plus 8, which gives me 8. So I get, again, 25 over 8, the exact same first term as I had in the previous iteration. And then I substitute in 1. So I get 6 squared, which is 36, over 1 plus 8, which is 9. And you can see that I am going to get exactly the same list of values for this sequence as I got for the sequence when written in a different way. So in this way, by pulling the index backwards to 0 by subtracting 5 and replacing each index in the sum end by pushing it forward by 5, we compensate for the change that we've made, and we generate exactly the same sequence. The next thing that we want to learn how to do is to strip out a finite number of terms. Now, why might this be important? When you're stripping out a finite number of terms, remember that we talked about the fact that when you have a sequence, an ordered list of values, that the head of the sequence, the first finite number of terms in the sequence, and it could be 10 billion, it could be a lot, but the first finite number does not affect the convergence of the sequence, that only the tail affects whether or not it converges. So there are times when the head of the sequence, the first finite number of terms, does not match the pattern of the tail of the sequence, the end of it, in which case we may want to chop off the head, set the head aside. It doesn't disappear, it just gets held to the side. And then we focus on just the tail of the sequence and looking at that part. In that case, we want to know how we do this with the notation. In other words, while it seems like this is pretty obvious, it does become pretty important when we're working with series. So here we have the series of a sub k starting with k equal 1 to infinity. We could have started with 0. We have a sub 1 plus a2 plus a3 plus a4 up forever. And notice that I could chop off the first two, a sub 1 plus a sub 2, and put them at the front, a1 plus a2 plus the sum of the sequence from k equal 3 to infinity of a sub k. And then I could use the technique that we used just a minute ago in order to rewrite this sum so that it begins at 0 again, but not forgetting that it does have these chopped off terms at the head. So it is possible to combine these two methods together. Now, what we want to talk about is the convergence of a series. When does a series converge? And what do we mean by converges? So when we're talking about convergence of a series, and again, we're talking about adding up the infinitely many terms of a sequence, what we're talking about with convergence is that even though there are an infinite number of terms in the sequence, when we add them together, we get a finite number. In that case, we would say it converges. And this, of course, is related to that sequence of partial sums that we talked about previously. So we want to look at the behavior of the sequence of partial sums, and we want to see if we can develop some intuition for this. If the sequence of partial sums converges, that means the limit of s sub n as n goes to infinity is a finite real number, then we say that the infinite series converges. So the convergence of the infinite series is actually given by the limit of the sequence of partial sums. And remember, the partial sums are just adding together, well, the first term by itself, S1, then the sum of the first two, S2, sum of the first three, S3, and so forth. So that creates another sequence, not the original sequence, but another sequence based on the partial sums. And if those partial sums approach a finite real number, then we say that the infinite series converges, and it converges to that value, S infinity. If the sequence diverges, then we say that the infinite series diverges, does not add up to a finite real value. Now, knowing the true value of an infinite series or an infinite sum, the S infinity, is actually extremely rare. We will only know this series for ones for which we can find an explicit pattern for S sub n. This is actually fairly unusual. In fact, there are only two types that we'll know for sure what the infinite sum is. Otherwise, our best option is an approximation. But because we can get the approximation to whatever degree of accuracy we want, this isn't really much of a hindrance. So we can approximate S infinity to whatever degree of accuracy we need. But again, knowing exactly what it adds up to is actually quite rare and typically only occurs with two specific patterns, which we'll look at today. That would be an infinite geometric series, where R is restricted to being between -1 and 1, not including -1 or 1, and also what's known as a telescoping series, which is based on rational functions. Before we get that far, we want to take a look at the patterns for S sub n, this nth partial sum. So if we can take this S sub n and we can find a pattern for it, and by pattern, we really mean a formula for S sub n in terms of the subscript n, then we should be able to take the limit of it as n goes to infinity, and then we can find the value. So if we're looking at this one right here, in example 2, can we find a pattern for the nth partial sum S sub n for the sum of n plus 1 divided by n? And this is a sum starting at n equal 1. So let's write out some terms for S sub n by first writing the sequence that it's based on, A sub n. So we're starting with n equal 1. So we actually have A1, A2, A3, A4, A5, A6, and so on. Now, what would these come out to be? Well, the formula for A sub n is n plus 1 over n, starting with n equal 1. So we start there. 1 plus 1 gives me 2 over 1. And then I end up with 3 over 2. And then I end up with 4 over 3. And you can see the pattern starting to develop here. The numerators and denominators are increasing by 1 each time. So we can see a pattern here, but this is not the sequence that we're concerned with when we're talking about the sequence of partial sums. This is the original sequence itself. The sequence of partial sums is adding together a finite number of these terms. Remember, S1 is always the first term by itself. So now we want to write down the sequence of partial sums. So S1 is 2. S2 would be 2 plus 3 halves, which turns out to be 7 halves. S3 turns out to be 2 plus 3 halves, plus one more term, which is 4/3, which of course is the same as 7 halves, plus 4/3, which turns out to be 29 over 6. Now, you may have to take a little bit of time to go ahead and prove that, in fact, those are correct. And let's write down at least another couple. So we have S4, which is going to be the 2 plus 3 halves plus 4/3. plus 5 over 4, which is 29 over 6 plus 5 over 4, which turns out to be 73 over 12 when you reduce it to lowest terms. So I'm basically getting the different values coming up. And in this fashion, I can go ahead and complete, and I can do S5. And S5 gives me 437 divided by 60. And I could even do S6, which is the sum of the first 6. And that would give me 169 over 20 when I reduce the fraction. Now, this is not the sequence of partial sums. So what does the sequence of partial sums look like? Well, the sequence of partial sums is just the ordered list of each of the partial sums. So 2, then 7 halves, then 29 over 6, then 73 over 12, then 437 over 60, and then 169 over 20, and so on. Now, in order to determine whether or not this converges, we would need some formula. We would need to be able to write S sub n in terms of some formula based on the values that we see here. Not the same formula that generated the original sequence, a separate formula. Now, if we look at these values and you were to write them in their decimal equivalents, doesn't it look to you as though these values are increasing and increasing without bound? In other words, they're getting a lot bigger as I go further out. They're not getting a little bigger, they're getting a lot bigger. Now we have in Desmos what's called a sequence of partial sums plotter. And I have the link in my notes, which would be right here. And so you can go out to the sequence of partial sums plotter, and it already has this particular one in it. And you'll see that what it does is it generates two plots, one that's here in orange and one that's here in black. The one in orange is the original sequence A sub n. So that is the list of numbers that we see up here: 2, 3 halves, 4 thirds, 5 fourths, 6 fifths, 7 sixths. Now that sequence of values appears to be approaching the value of 1, and in fact it does. And you can see that the discrete orange dots are getting very, very close to the horizontal asymptote y equal 1. Now, as they get closer and closer to 1, it becomes closer and closer to that value. We would say that this sequence converges to 1. But if you think about that, then that would probably mean that this sequence of partial sums blows up to infinity. In other words, the series probably diverges. Why? Well, you start with these values at the beginning, finitely many. That's the head, you chop them off. But at some point, all these values in the tail are practically 1, but there are infinitely many of them. And you know that if you add 1 over and over infinitely many times, it's going to blow up to infinity. Never mind that you still have to add the head of the sequence on. And that seems to indicate that because the sequence is approaching 1, the series must be approaching infinity. And in fact, what you see here in the black dots is the second column of the y values in the table, third column, which gives you, of course, the sequence of partial sums. So that's what these values are here on the far right. And this is the first 1, 2, 3, 4, 5, 6 partial sums that you see here. And you can see it looks like they're increasing. And then I zoomed out so you could get more of them on this graph. And you can see that, in fact, even though the sequence, the original sequence, approaches 1, the sequence of partial sums is approaching infinity. S infinity is approaching infinity, which is not a finite real number, so we say it diverges. And because it diverges, we would say that the series diverges. Now, the next thing that we want to do is talk about a geometric series. There's a particular pattern to the geometric series, and geometric series turn out to be probably the most important series that we study because many of the techniques we'll use to determine convergence of the series depend on this geometric series pattern. And so it's important that we understand the pattern. Remember that our pattern here is a first times r to the n. A first could just be 1, but it could be some other constant. It's just a constant. A first is a constant. We typically want to start at 0 because it makes our formulas better, not because we have to, but because it makes the formulas simpler. So we tend to start geometric series at n equals 0. So we have a sub 0 r to the n. And this is going to generate the sum of a first plus a first times r, a first r squared, a first r cubed, and so on. Remember, for a geometric series or a geometric sequence, to get from one term to the next, you multiply the previous term by the common ratio r. So each one gets another r multiplied on it. Now, we want to do some manipulation, and probably at first it won't make any sense what we're doing, but we're trying to come up with a formula for these. So in order to derive a formula for these, and again, this took someone weeks, months to figure out, we're going to multiply s sub n by r. So we take s sub n, which is the sum of the first n terms ending in a first r to the n minus 1, and we multiply through by r, so that it increases the power on r in every term, so that now we have r to the first in the first term and r to the n in the last term. Now we want to subtract the expression for s sub n, which is right here, from this expression for r s sub n. So we want to compute r s sub n minus s sub n. So here's r s sub n, which is this one right here after multiplying through by r. And we want to subtract this one, which is below it. Now, you can tell that they have a lot of terms that are in common, but not all. A first by itself is not a term in r s sub n. And the last term in r s sub n, a first r to the n, is not a term in s sub n. So even though most of the terms are common between the two, not all of them are. When we subtract s sub n from r s sub n, the common terms are going to cancel each other out. We're going to get a lot of cancellation, and we're going to end up with a first times r to the n minus a first. And if you're not seeing the cancellation, I have a picture of it here with each of the like parts being added out. And it looks like my things have scooched over a little bit, but you can kind of see where it comes through, and we get a first, r to the n minus a first. Now, let's rewrite what we've done. We took r times s sub n, and we subtracted s sub n from it. And we got a formula for that of a first r to the n minus a sub first. Remember, we're trying to come up with a formula in terms of n and maybe a first to express s sub n. If we can find a formula in terms of the subscript, the index n, and maybe a first for s sub n, then we can take the limit of it as n goes to infinity, and we'll know whether or not it adds up to a finite value. So the first thing we do on the left is we factor out the common factor of s sub n, and that gives us s sub n times r minus 1. On the right, we factor out the common factor of a first, which gives a first times the factor r sub n minus 1. Now you know where I'm going, right? We're trying to find a formula for s sub n. Note that what we're going to have to do is divide both sides by r minus 1. When we divide by r minus 1, we are automatically saying by doing so that we cannot allow r to be 1. Because if we do allow r to be 1, we would have division by 0, which is a huge no-no. But throwing out r equal 1 is not a big disadvantage, because remember in the previous video, when we talked about sequences, when we allowed r to be 1, all the values just became 1. 1 to any power, finite power, is 1. And so it was sort of boring. It was just the constant 1. And we already know if it's always 1, the series will diverge, because 1 plus 1 plus 1 forever and ever blows up to infinity. So we know that doesn't converge. So eliminating 1 is not a big hindrance to us. Now you'll see this is written r to the n minus 1 over r minus 1, but in the second form, and this is the form that you're most likely to see in any textbook, we have reversed the order of both parentheses. And in essence, what we did was we factored out a -1 from each set of parentheses, and a negative divided by a negative is positive. So this is equivalent to the first, with a caveat that r cannot be 1. Do we have a formula for S sub n? Yes, we do. We have a formula for S sub n, which depends on a first, which is a known constant. We'll see it at the front of the sequence. So we'll know what a first is. And it also depends on r. But again, r will be known because they'll have to write down what the summand is. We'll be able to see a first and r more or less by inspection. And then it depends on n, which is the index. Again, n is representing the domain variable, the thing that's changing, but in our case, changing by discrete values, one apart. So this gives us something for S sub n. And then we can take the limit of this as n goes to infinity. Now, what do you think we're going to get as we take the limit as n goes to infinity? Let me write out what you would have here. So we have the limit as n goes to infinity of S sub n, which becomes the limit as n goes to infinity of a first, whatever that first number in the sequence is, 1 minus r to the nth over 1 minus r. Now, r is some value that's being raised to the power. So like an exponential function. Now, we've got this expression right here. We need to consider different values of r. Now, if r turns out to be greater than 1, remember what we saw in sequence or section 5.1 when we were talking about sequences. If we allow r to be greater than 1, then r to the n goes to infinity. In other words, it diverges. And if it diverges, then we know that the series, the sum of it, is going to diverge as well. If r is less than -1, we know it also diverges. The even scripted terms go to positive infinity. Odd scripted terms go to negative infinity. And since they don't agree, evens go one place, odds go somewhere else, then we say that the sequence doesn't converge. When r is -1, the sequence diverges again, even subscripted terms going to 1, odd subscripted terms going to -1. And of course, when r is 1, we know the sequence approaches 1, but adding 1 together infinitely often is not finite. In other words, of all the possible values for r, and again, we're looking at the number line here, and we're looking to break it up into different regions. We know right here, the series will diverge. And we know at -1, the sequence doesn't even converge, so it diverges. And we know down here it diverges. And we know up here it diverges. And that only leaves us with one location. And that's the place here between -1 and 1. And that becomes the sweet spot for the geometric series. So now we want to think about what happens to this when we restrict r to being between -1 and 1. Now, this can be written a couple of different ways. You can write it like this with a 3-part inequality. You can also write it in this following fashion, that the absolute value of r is less than 1. And that means exactly the same thing, that r is between -1 and 1 and not equal to either one of them. Now, what kinds of numbers do we have here? Well, if we're talking about the numbers between -1 and 1, we're talking about proper fractions, right? The numerators are smaller than the denominator, either the positives or negatives of those. So numbers like 2/5, 1/5, 1/2, -1/2, -3/5, all proper fractions and all between -1 and 1. Now, if I take a fraction, a proper fraction, and I raise it to a power like n, what happens to r to the n as n goes to infinity? Well, let's imagine, if you will, what would happen if we took something like 1/2 to the n, and then we took the limit as n goes to infinity. Now, what is that going to do? Well, we've got this 1/2, then 1/4, then 1/8, then 1/16, 1/32. As long as it's a proper fraction, what is it approaching? Well, as n goes to infinity, it's approaching 0, which means that this part right here is going to go to 0. And this will leave us with the formula a first divided by 1 minus r, with the restriction that r be between -1 and 1. And we're going to see this a little bit later on as well. We'll go through this a little bit more. In other words, the geometric series will converge to a finite number. I know this just blows your mind. I'm taking infinitely many numbers, none of which is 0, even though they're very, very close to 0. I'm adding them together and I get a finite number? How can that be? But it works, provided that r is between -1 and 1. So here it is written out in a better non-handwritten format. So for a geometric series, if the series is finite, meaning the sum from k equals 0 to n minus 1, we get S sub n as a first 1 minus r to the n over 1 minus r. If you have a finite number of terms, you can't ignore that r to the n because it's not going to go to 0. If the infinite series has magnitude of r between -1 and 1, absolute value less than 1, then we know that our formula becomes a first over 1 minus r. Because since r is a proper fraction, raising it to the nth power as n goes to infinity leads to 0, so that part drops out. If the magnitude is greater than or equal to 1, -1 or 1, or above or below, we know that it diverges. It blows up to infinity. In other words, we always know what the pattern is for an infinite geometric series. These are one of the two where you can say exactly what the value of it is. Now we want to take a look at that with example 2. We want to come through and we want to prove that the repeating decimal 0.99999 forever is precisely, not approximately, but precisely equal to the number 1. And you may be saying, but that's not true. That can't be true. It's a repeating decimal, 0.99999, forever and ever. All digits are 9 and it goes forever. Well, actually, it is true. It's exactly 1. And the way to prove it is to use an infinite geometric series. So we're going to start with the decimal number, which we can write as 0.9999 and so on. And what we're going to do is we're going to write each digit in its representative fraction form. So the first decimal place, of course, is the tenths place. So that represents actually 9/10. And the second digit in the second decimal place represents 9 divided by 100, so 9/100. And the third 9 in the third decimal place represents 9 1,000. And the fourth one represents 9 10,000, and so on. We could continue in that pattern forever and ever. So what I've done is I've taken the decimal value, repeating, and I've written it as the sum of a bunch of fractions. Now, if I'm looking at that, notice that all the numerators are 9. Now, the denominators are not all the same, but the numerators are all the same, which makes them common, which means it's a common factor, which I can factor out. So the next thing I'm going to do is simply factor that out. So now I've got, well, I'm having some trouble getting it to write. Messing up on me. So I take the 9 and I factor it out, and that gives me 1/10 plus 1 over 100, plus 1 over 1,000, plus 1 over 10,000, and so on. Now, can you see what's happening now that we have it written in this form? This is the sum of a bunch of numbers. It's an infinite sum, so it looks like a series. Could I make a sequence of these? 1/10, 1 over 100, 1 over 1,000, 1 over 10,000, yes. So I can think of this as an infinite series if I can find a pattern for it. And the pattern is start with 1/10, and to get to the next one, multiply that by 1/10. And that will give me 1 over 100. Then if I multiply by 1/10 again, I get 1 over 1,000. And if I multiply by 1/10 again, I get 1 over 10,000. In other words, this is a geometric series where the common ratio, taking 1 over 100 and dividing by 1 over 10, would give me 1/10. So the common ratio is 1/10. So in essence, what I have here is 9 on the outside, and then I have my 1/10, the first value, that's a first, times 1/10 to the nth power. In other words, to get from one to the next, each time we're going to multiply by 1/10. Now, to write it in this form, I'm assuming that n is going to start with 0. So this is starting from n equals 0 and going to infinity, which would generate that list of fractions you see above. So this becomes the sum of 9 times this factor. So the 9 stays on the outside, and we have the sum from n equals 0 to infinity of 1/10 times 1/10 raised to the nth power. And this is what we have. So based on this, again, I said that you will know what a first is and you'll know what r is. You can see them. When n is 0, the 1/10 to the 0 becomes 1, and so a first is just 1/10. The 9 is a constant factor on the whole geometric series, so it stays on the outside. So a first is 1 over 10, and r is the base being raised to the power. So it's the 1/10 being raised to the nth power. So we have a first is 1/10, and r is also 1/10. Now we can use our formula, and remember that our formula for s infinity, which is the limit as n goes to infinity of s sub n, which gives us s infinity, is a first over 1 minus r, provided that r is between -1 and 1. So for r between -1 and 1, we have this formula a first over 1 minus r that we can apply to the series part. So we have the 9 at the front, still hanging out, times a first, which is 1/10, divided by 1 minus 1/10. Now, 1 minus 1/10, you need a common denominator, which is 10. So 10/10 minus 1/10 gives you 9/10. So we still have the 9, 1/10 divided by 9/10. And of course, you have a complex fraction. So remember that you take the denominator fraction, take the reciprocal, and multiply by it. So this becomes 9 times 1/10 times 10/9. So this becomes 9 times 1 over 10 times 10 over 9. Notice the 10s cancel and the 9s cancel, and you get 1. Not approximately 1, you get precisely 1, which means that the value of the infinite series, the infinite sum, is exactly 1. I know, it sort of blows the mind, doesn't it? Let's take a look at another example. Let's now look at example 3. We want to use a geometric series again to find a precise rational number for the repeating decimal 0.237, 237, 237, 237, and so on. So the pattern is that it repeats the digits 237 forever and ever. all repeating decimals can be written as rational numbers. In other words, the ratio of two integers, all of them. So we can use what we've learned about geometric series in order to come up with that rational number that represents this repeating decimal. So what we're going to do is we're going to start the same way that we started last time, and we're going to use the pattern, which in this case is 3 digits long, and we're going to split the repeating pattern into fractions. So the first 3 take up the first 3 decimal places. So it's 237 divided by 1,000. Remember, for each digit that you have behind the decimal point, you need a 0 in the denominator. And now the next group of 237 has to be over a 1 followed by 6 zeros because there are 6 decimal places. So 237 over a million. And then the next one, of course, would be another 237, but this would be over a billion. We would have to have 9 zeros following this one. And the pattern repeats, okay? So we could have another 237 over 1 over with 10 times 10 to the 12th. We would need 12 zeros. So this is our repeating pattern. Notice the 237 is common to every term. That makes it a common factor. So we're going to factor the 237 off. So this leads to 237 at the front. And then we have 1 over 1,000 plus 1 over 1 million plus 1 over 1 billion, and so on. Kind of getting carried away with the zeros here. And I could rewrite this one as well. And another way of writing this, of course, this would be 10 to the 3rd, and this would be 10 to the 6th, and this would be 10 to the 9th. So this must be 10 to the 12th, and so on. In other words, if you look at this, you can see the pattern that's developing. It's increasing by 3 each time, which makes sense because the repeating pattern is 3 digits long. So I need to multiply by 1 over 10 to the 3rd, or 1 over 1,000, to get from one term to the next, to the next, to the next. Now the 237 isn't a part of the infinite series, but the rest of it is, where a first is the 1 over 1,000, which is this term right here. So we have 237. And then we're going to have the sum from n equals 0 to infinity of 1 over 1,000, that's a first, times 1 over 10 to the 3rd, or 1,000 again, being raised to the nth power. And that would generate the same numbers. So this is a geometric series. A first is 1 over 1,000, and R is 1 over 1,000. That is not always going to be the case. They're not always the same. They have been in the last two, but they're not always the same. And I think in the next example, they're different. So we have this, and we know that because R is between -1 and 1, that we can write this using the formula A first over 1 minus R. So S infinity for R between -1 and 1 becomes A first over 1 minus R. Now that's only true for the ones between -1 and 1. It's not true for any other values of R. And this lets us rewrite this infinite sum as 237 being multiplied now by A first, which is 1 over 1,000, divided by 1 minus 1 over 10 to the 3rd, or 1 over 1,000. Now we need to rewrite what this comes out to be. 1 minus 1/1000th, of course, would be 999 over 1,000. So we end up with 237 times 1 over 1,000 over 999 over 1,000. And then when you flip and multiply, you get 237 times 1 over 1,000 times 1,000 over 999. You've got some reducing to do here. You know the 1,000 goes into each one of those and they cancel. 999 is clearly divisible by 9, so of course it's divisible by 3. What about 237? 2 plus 3 is 5. 5 plus 7 is 12. 12 is divisible by 3, so this is at least divisible by 3. And when you reduce it, you do end up finally with 237 over 999. We need to divide by 3. So if we divide this by 3 and divide this by 3, I get 79, which is prime, over 333. And this would be the reduced fraction, which represents the repeating decimal number 0.237237237. So hopefully this makes sense to you, what we're doing so far, how we're using infinite geometric series with ratios between -1 and 1 to find the rational number for a repeating decimal. We want to take a look at one more example where not all of the digits repeat, where the repeating pattern is just found in the back part of it. So we're going to take a look at this one now, which is example 4. We want to find the precise rational fraction or rational number for 3.41237237237. So it's, again, 3 digits long, which must mean that when we go from one to the next, we're multiplying by some form of 1 over 10 to the third, probably. Now, first thing we need to do is rewrite this as a series of terms added together, and the ones after the decimal point will become fractions. So we're going to go until we reach the repeating decimal, and then the repeating pattern stays together over the denominator corresponding to where the decimal places are. So this is going to become basically 3 plus 4 over 10, which doesn't match the repeating pattern, plus 1 over 100, so you could write it as 41 over 100 if you really wanted to, plus, and now we've reached the repeating pattern. So 237 now has to go over 100,000. Now, why 100,000? Come over here and count where that repeating pattern stops. It's in the 5th decimal place, which means I need 5 zeros in the denominator. And then the next pattern, of course, is going to be 237. And then I'm going to need another 3 decimal places. So I've got 100 million. And then, of course, it repeats again after that. Now, again, what we're doing here is we're finding a pattern that repeats. Now, the beginning doesn't fit that pattern, and that's okay. We're just writing out what it is. This part right here is going to form the head of our sequence, which we're going to chop off and set aside because it doesn't match the pattern of the back. And the pattern of the back is the convergent geometric series. So the pattern of the back then, which is the tail, is this one, 237 over 10 to the 5th plus 237 over 10 to the 8th plus 237 over 10 to the 11th plus ... and so on. So now we again go ahead and we try to write this as an infinite series added to the head. So in essence, we can go ahead and write this 3 plus 4/10 plus 1 over 100. That's the head. Plus, we factor out the 237, and then we have the sum. Our first is going to be 1 over 10 to the 5th. That's the first value. And then our common factor, our ratio, is each time to go from 1 to the next, we multiply by 1 over 10 to the 3rd. And this is going to be raised to the nth power, where n begins at 0 and goes to infinity. So again, we factored out the 237, which left 1 over 10 to the 5th, 1 over 10 to the 8th, and 1 over 10 to the 11th. So the first term in the geometric series part, the tail, is going to be 1 over 10 to the 5th. And then to get from one term to the next, you multiply by 1 over 10 to the 3rd. Now, this is definitely a value that's between -1 and 1. So we know that we can use the formula A first over 1 minus R for the convergent sum of the series. So now we can go ahead and repeat this. and we can write down what it is equal to down here at the bottom. And this gives us the following. Now I'm going to write this as 3 plus 4/10 plus 1 over 100 again. That's the head of the series that we had to chop off, plus 237 times a first, 1 over 10 to the fifth, over 1 minus r, which is 10 to the third. Now, let's just look at the fraction part, since this is a lot of rewriting and rewriting. If we just look at the fraction part right here, what I've highlighted now in pink, then I know that I can think of this as 1 over 10 to the fifth times 999 over 1,000. That's 1,000 over 1,000 minus 1 over 1,000, or 999 over 1,000. Now I need to write these out, and remember that we're going to take the numerator fraction and multiply by the reciprocal of the denominator. So this is going to give me 1 over 100,000, which is 10 to the fifth, times 1,000 over 999. Now these three zeros cancel those three zeros, and I end up with 999 times 100. And that will give me 99,900. So now putting this all together with what I have before, I have 3 plus 4 over 10 plus 1 over 100 plus 237 times 1 over 99,900. Now, in order to represent this as a rational number, we need to get a common denominator, which of course would be the 990 or 99,900, except I believe that 237 we said is divisible by 3. So we'll go ahead and reduce this fraction. And when we reduce this fraction by dividing by 3, we end up with 79 in the numerator and 33,300 in the denominator. So then we can combine these fractions here into a like fraction and combine it with this. And when you do quite a bit of work and you end up putting them all together, here's what you end up with. So 3 gets rewritten as 99,900 divided by 33,300. And then the next one, the 4/10 and the 100th, I can think of this together as 41 over 100. And when I rewrite that as a common fraction over 33,300, I get 13,653 over 33,300 plus the 79 over 33,300, so that my final expression for the rational number that represents that repeating decimal is 28,408 divided by 8,325. Notice that there was some reduction that happens. So you can try it. Go ahead and put this into your calculator and see that it does in fact generate that decimal number that we had up here at the beginning. Right? So this is how we can use an infinite convergent geometric series to rewrite a repeating decimal in terms of its rational number, which is actually quite convenient in some cases. And it gives us an expression that is not repeating as a decimal. Now we want to look at the other type of series for which we can actually find the convergence sum. So we've been finding convergent geometric series sums. And now what we want to do is look at the other kind of series for which we can actually find the value of the infinite sum. There are only two types we can do this for. The geometric series where r is between -1 and 1, which gives us a first over 1 minus r. We know that's s infinity. And now the second pattern, which is called the telescoping series pattern. So it's not based on a geometric series. Instead, it's based on rational functions. So again, we need to come up with some kind of formula for S sub n in terms of maybe the first one and n, so that we can take the limit as n goes to infinity, so we can find the actual value of S infinity. Now, telescoping series result from the difference of rational functions. Now, remember, a rational function is the ratio of two polynomials. So the coefficients are real numbers. Pi is fine, square root of 5 is fine, but the square root of -2 is not fine. That's not real. And the powers on the variable have to be whole numbers. 0, meaning you could have a constant, or 1, 2, 3, 4, 5. They've got to be whole numbers. So no variables in the denominator. We take the ratio of two such expressions, and that gives us a rational function. Now, what happens in our representation of S sub n is that all but a finite number of the infinite number of terms cancel out. In fact, we end up usually with 1 or 2, 3 at the front, 1, 2, or 3 at the back, and all the ones in the middle kind of collapse out, which is what we saw when we did R times S sub n minus S sub n in the geometric series. And this is very similar to an old-fashioned maritime telescope that you extend out and collapse back down. So we're thinking of this as a telescoping series because it collapses and you get the piece at the beginning and you get the piece at the end, and everything in the middle disappears when you collapse it. And that's the name, or where the name comes from. So when we have this, they're relatively easy to spot because the summand looks like a rational function. So it's the ratio of two polynomials, and something that you would normally use partial fractions to decompose. And so we are going to use partial fractions to decompose it. Now, when we write out the expression for S sub n, we'll have to write out 5, 6, or even more terms at the beginning, and the same number at the end. So the last one we'll write is S sub n. So if we're going to write 5, I'll have S sub n, and then S sub n minus 1, that's 2, S sub n minus 3, S sub n minus 4, and S sub n minus 5. So I've got to write the n minus 5, n minus 4, n minus 3, n minus 2, n minus 1, and the nth term in S sub n in order to get 6 terms written at the back. So we have to be kind of careful when we do this. Why do we have to write out so many? Well, sometimes it's hard to see the telescoping pattern, to see that pattern of cancellation where things knock each other out. So you have to just keep writing terms until the pattern of cancellation becomes obvious. Now let's take a look at example 5. So be prepared, we're going to have to do a partial fraction decomposition. So again, you can either use the Heaviside method, you can use choose wisely, or you can use the equating coefficients method of solving this. The first thing we want to do, of course, is rewrite this. And we don't have to start at 0, we can leave it starting at 2, but we want to rewrite it with a factored denominator. So we get k minus 1 and k plus 1. And again, the k is immaterial, it could be n, but because I'm going to represent S sub n, I wanted to use a different index for the summation. So I have these two right here. Now I know, because this is a rational function in k, that I can use partial fractions to write this as the sum or difference of two simpler rational expressions. So I know, because I have one distinct linear term, k minus 1, that in fact, this has to be equal to the sum from k equal 2 to infinity of sum a over k minus 1 and sum b over k plus 1. So I want to just focus for a minute on the partial fraction decomposition. Again, you can use whichever method you want. I'm going to focus on choose wisely. That's my preferred method. So I have 1 over k minus 1 times k plus 1. And this is equal to a over k minus 1 plus b over k plus 1. And I'm going to multiply all three terms here by the lowest common denominator, k minus 1, k plus 1, on each individual term. And then this will get rid of the fractions and will give me an equivalent equation. So this gives rise to the following equation. On the left, all that's left is the numerator 1. On the right, I have A equal times K plus 1 plus B times K minus 1. Right? And then I choose wisely. So the first thing I'm going to choose is K equal negative 1. And if K is a negative 1, then this term drops out completely. And I get negative 2B equal 1. So choose K equal 1. And that leads to 1 equal negative 2B, which implies that B is a negative 1/2. And then I can choose wisely again. And I choose the other 0, which is negative 1. And when I choose negative 1, the K plus first term drops out. Did I do that backwards? I did do that backwards. Let me repeat that. When I choose K, I was doing minus 1. When K equal 1, this term drops out. And I get A times 2, which would tell me that A is 1/2. So I actually did these in reverse order, wrote one and did the other. So when K equal 1, I get 1 equals 2A, which implies that A is equal to 1/2. Right? So I have A is a half and B is negative a half. Right? So be sure that you know which one is which. I started doing K equal negative 1 and forgot and wrote K equal 1. Okay, so now that we have this expression, I can replace the A and B in this expression, which means that I can replace it up here in this value up here. So I've got this 1/2 on the whole thing. So now rewriting, I have the sum from K equal 2 to infinity of 1/2 over K minus 1 minus 1/2 over K plus 1. Now, the 1/2 is a constant, and we can pull the constant out. We're going to take a look now at a finite sum. Now, for an infinite sum, we don't yet know whether or not we can take out the 1/2. We're going to talk about that in a minute. But what I want to come up with is not the infinite sum. I want to find a pattern for S sub n. So find a pattern for S sub n. Now that is the nth partial sum, and S sub n is equal to the sum from K equal 2 to n of this 1/2 over K minus 1 minus 1/2 over K plus 1. Now, because there's a finite number of terms, and that could be 10 billion, but because there's a finite number of terms, the 1/2 becomes a common factor, which I can factor out. When there are infinitely many, there's no guarantee yet that you're allowed to do that. So you can't do that here where it's going to infinity, but we can definitely do it here where there's a finite number. And this is going to give us 1/2 times the sum from K equal 2 to n of 1 over K minus 1 minus 1 over K plus 1. Now we want to write out some of these terms and see if we can find a pattern. So again, we are writing down what the pattern for S sub n is. We have a 1/2 at the front times everything that comes after. So we're going to have great big brackets and everything inside is multiplied by 1/2. So now we're going to go through and we're going to write out some at the beginning until we can start to see the cancellation pattern. And then we'll write out the same number of terms at the back so we can see the cancellation at the back as well. And by front, I mean we're going to start with K equal 2. And we're going to go K equal 2, K equal 3, K equal 4, K equal 5 until we can see the pattern of cancellation. So I'm starting here with K equal 2. So now, when I have that and I replace it in here, I get 1 over 2 minus 1, which is 1 over 1. So I can write this as 1 over 1 minus 1 over 2 plus 1, which is 1 over 3. All right, that's the first set coming from k equal to 2. So I have 1 over 1 minus 1 over 3. There's no cancellation yet, so keep going. Now the next set is going to come from k equal 3. And again, we may have to write out 5 or 6 of these, so maybe up to k equals 7 or 8. So when k is 3, I get 1 over 2 minus 1 over 4. Still no pattern that I can see. So I keep going. K equal 4. So keep writing these out. This is going to give me plus 1 over 3 minus 1 over 5. Now I see the first inkling of some kind of cancellation pattern because I had a minus 1/3 here and I have a plus 1/3 here. So I'm starting to see that there may be a pattern of cancellation. So I'm going to go ahead and write out some more terms. You can now see that there is a repetitive pattern here. So the next one should be 1 over 4 minus 1 over 6. And then the one after that should be 1 over 5 minus 1 over 7. And that's for k equals 6. So we've written out the first 5, allowing the subscript to be 2, 3, 4, 5, and 6 in turn. Now, do we see a pattern of cancellation that's going on here? Yes. Notice that the 1 is not canceling out and the 1/2 is not canceling out. In fact, what's happening is this negative 1/3 term is canceled by not the next positive, but the positive after that. So it's like you've got to jump over 2 positives to get to that canceled factor. So in essence, this one right here is canceled by that right there. And then the next negative value, negative 1/4, is canceled not by the next positive term, but by the positive term after that. And then I could find the next one. I've got a negative 1/5, which is canceled by the one after that. Now, would the negative 1/6 cancel? That's the question that we haven't answered yet. Well, I've got a plus dot 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 plus, which means that somewhere in that dot dot dot, the negative 1/6 and the negative 1/7 would cancel because in this dot dot dot, I'm going to have those following positive terms, which are going to cancel with them. Now I want to start at the back and I want to write out at least 5 terms at the back. That the last one's going to be S sub n, then in front of that I have n minus 1, n minus 2, n minus 3, n minus 4. So I want to start with k equals n minus 4. So we're going to start with k equal n minus 4, and I'm going to substitute that value in place of k. So I have 1 over n minus 4 minus 1, which becomes 1 over n minus 5. Minus, and then the next one, n minus 4 plus 1 would be n minus 3. Did I write that correctly? N minus 3. Right? So now what do we have for the next one? Well, let's go for the next set. I think I did that right. 4 is n minus 5, 1 down, 1 up. And then the next pair is going to be k equal n minus 3. So I'm going to add that on. N minus 3 minus another 1 would be n minus 4 minus 1 over n minus 3 plus 1 would be n minus 2 plus. So these came from n minus 3. And now I'm going to do n minus 1, k equal n minus 2. So n minus 2 minus another 1 would be 1 over n minus 3. Notice we've got some cancellation developing. Minus 1 over n minus 2 plus 1 is n minus 1. And notice that we've got a pattern here. We've got 5, then 4, then 3. And this is going 3, then 2, then 1. So we've got a pattern developing. So we could write the next terms using the pattern, but we can also keep plugging them in. And then we want to do k equal n minus 1. So this becomes 1 over n minus 1 minus another 1 would be n minus 2 minus n minus 1 plus 1, which would be 1 over n. And then the last one I want to do, which I'm going to, I have space, is the nth one. Remember that when we do Sn, we stop at the nth one. So this is really n-2 because we didn't, or n-1 because we didn't have it first, but we're going to stop at s sub n. All right. So when we're looking at this, we have k equal n. And when we're looking at that, we have 1 over n-1 minus 1 over n plus 1. And we're going to stop there. So what I was saying a minute ago was normally when we have Sn, there should be exactly n terms. But because this started at 2, we're actually going to have n-1 terms. So you could go out one more, or you, again, because we're taking the limit, it doesn't really matter because we're taking the limit as n goes to infinity. Now we want to look for a pattern of cancellation down here as well. And notice that we have this plus n-5. Well, positive terms are canceled by the negative 2 hops to the left. So there must be something in this dot, dot, dot that cancels this 1 over n-5. So it's going to be gone. In the same way that these values up here, this 1 over 6 and 1 over 7 get canceled by something in the dot, 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 this 1 over n-5 gets canceled by something in the dot, dot, dot. Now, what about the 1 over n-3? Well, these two cancel each other out. So I've got cancellation of here and here. And then I've got 1 over n-4, but it's positive, so it would have been canceled by the term in front of this. And so I know that it also got canceled by something in that space. So this got canceled by something in that dot, dot, dot. And then what about the 1 over n-2? Well, they cancel out as well. So drawing little circles here, these guys get canceled out. And what is left? What does not get canceled? Well, again, this negative 1 over n-1 can't get canceled because it would be canceled by the next positive term, which I don't write because I'm writing s sub n. And what about this negative term? Well, it doesn't get canceled because it would be canceled by the 1, 2 down the road. So it's not gone. And these don't get canceled because they would have to have something to their left. And there's no negative terms to their left. So everything telescopes, it collapses down so that we're left with 2 terms from the beginning and 2 terms from the end for this representation of s sub n, or s sub n-1 technically. So now let's write down what this comes out to be. So we have s sub n is equal to 1/2 times 1 plus 1/2 minus 1 over n-1 minus 1 over n. Now that's a representation, a pattern, if you will, or a formula to represent s sub n. And then to find s infinity, we need to take the limit of that as n goes to infinity. So s infinity, which of course is the infinite sum that we started with, the sum from, what was it again? I've lost track. K equal 2 to infinity of 1 over k squared minus 1 has got to be equal to the limit as n goes to infinity of s sub n. Now, in order to take the limit of this expression here for s sub n, remember the 1/2 is a constant. You can always take a constant out of a limit. And the limit of a sum or a difference is the sum or difference of the limits. So I can take the limit of each individual term. So this becomes 1/2 times the limit as n goes to infinity of, well, 1 plus 1/2 is 3/2. And the limit of a constant is the constant, so I'll get 3/2, minus the limit as n goes to infinity of 1 over n-1, minus the limit as n goes to infinity of 1 over n. Now, what happens with the second two? They're simpler rational expressions, simpler rational functions with a linear factor in the denominator. And because they're bottom heavy, the degree of the denominator is 1, the degree of the numerator is 0. As n goes to infinity, both of these are driven down to 0. And we learned that when we learned to evaluate limits in Calculus 1. And that leaves us with the expression 1/2 times the limit of 3/2, which of course is just 1/2 times 3/2. And so this turns out to be 3/4. Now, you may be asking yourself, yeah, but what does that mean again? Well, this is an infinite sequence here. And when we add all the terms of that sequence together by taking the series, we get the sum of an infinite number of numbers. And that infinite sum adds up to exactly 3/4. That sum of an infinite number of numbers adds up to the number 3/4. That finite real value. And that's a way that we can use a telescoping series in order to find the exact value of the series. Now, we can only find exact values of series for two types that we know of. That's the geometric series, where r is between -1 and 1, which gives us a first over 1 minus r, or a telescoping series, where we can rewrite a rational summand into the sum or difference of simpler rational functions, and we get a telescoping behavior. Now, you can bet on an exam I'll ask you for one of each of these, so be prepared for that. Now we want to talk a little bit about the algebraic properties of convergent infinite series. You'll remember that when we were working this one, I said you shouldn't factor the 1/2 out while we were working with the infinite series, because we don't know if we're allowed to do that. If you have an infinite number of numbers, can you really factor out the constant? Well, the answer is you can, only when you know it converges. And we did not know that it converged. So if you don't know if it converges, then you cannot factor out the constant. You have to leave the constant on the inside. So in this case, we're going to let the series of a sub n from 0 to infinity and the series b sub n from 0 to infinity both be convergent series. In other words, this infinite sum adds up to a finite number, and this infinite sum adds up to a finite number. Then, knowing that they are convergent, the series of a sub n plus b sub n will converge, and you can split up the sum because you already know that these individual ones converge. But you have to know that first. Now, this works whether they are added together or subtracted together. And it also means that you can factor out the constant. But you can only factor out the constant when you already know that this series converges. If you don't know, you need to leave it in there. Now, is it possible for two series, a sub n and b sub n, from 0 to infinity, to individually diverge? And yet, if you added them or subtracted them together, that series would converge. And the answer is yes, it's possible. So it is possible to take two divergent series, add them together or subtract them, and to get a convergent series from their sum or their difference. So it is possible. Basically, the end rule thumb is to split apart the summands of a series, you have to know in advance that they converge. Otherwise, don't split them apart. These rules only apply to convergent series, so we can only split them when we already know they converge. And the same is true about pulling out the constant. It doesn't mean that it doesn't hold, we're just not guaranteed that it holds. Now we can come to the final discussion in today's topic of series, which is the harmonic series. We want to talk about what the harmonic series is. It's a very important series. Geometric series are probably the most important series because many of the tests for convergence depend upon that pattern. But the harmonic series is also a very important series that you need to just memorize what it is. It's based on the rational function 1 over x, and the sequence becomes the list of values 1 over n. So the sequence a sub n is simply the list of values from 1 to infinity. So 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5, and so on. And you can see quite clearly that the sequence itself is going to converge towards 0. The values are getting smaller and smaller and approaching 0. And because they're getting smaller and smaller and they're practically 0, when we add them up, it could be possible, not guaranteed, but possible, that the infinite series adds up to a finite number, but in fact it does not. The harmonic series is sort of the boundary function between ones that do converge and ones that don't. So it diverges as a series, but it diverges very slowly. So the sequence of partial sums does go to infinity, but it does so in a relatively slow manner. So we will prove in the next video that this series diverges, but for now you'll have to take it on faith. In order to give you sort of a feel for what's happening, though, I went ahead and produced it on the Desmos sequence of partial sums plotter. So you can see the points on the actual sequence here in the orange dots. You can see they're approaching 0. And the sequence of partial sums is noted here with the series of discrete black dots. And you can see that it is growing very slowly. It is heading towards infinity, but very, very slowly. So the harmonic series is a very important series because it's sort of that boundary series between ones that get low enough fast enough so that their infinite sum is finite and ones that don't. So it's sort of the boundary series, if you will. If you want to learn more about why we're studying series and why series are so important, I recommend that you watch the video by 3 Blue, 1 Brown on Taylor series, where it does an introduction. And it gives a really good feel for why we might want to use series in engineering or physics or mathematics. So I hope that you'll join me in the next video when we're going to be taking a look at something called the integral test and the divergence test, where we'll actually prove that this sequence of partial sums for the harmonic series does in fact diverge.